All right, we'll move on. The next speaker is Kevin Schlaufman, and he will talk about comparing photospheric elemental abundance trend with condensation temperature unrelated to terrestrial or giant planet formation. And I'll give you a 1-minute reminder, but I think we've all been pretty on time. So take away when you're ready.
Great, thank you. So one way to put the solar system in context is to compare the sun to other nearby stars, because we can tell, at least on average, what the initial conditions of planet formation were by looking at the elemental abundances in the photospheres of main sequence dwarf stars. So the project I'm going to tell you about today is mainly the work of a former JHU undergraduate, Chris Wang. He just began as an astrophysical sciences PhD student at Princeton. So one of the earliest observations that was made in this context, that is, how is it the sun compares to other nearby stars for the context of planets and planet formation, is illustrated here on this diagram. So this is on the left-hand side, the atomic number, on the right-hand side, the condensation temperature. The y-axis is the average spectroscopic abundance of the sun compared to solar twins. And it was found that compared to nearby stars that were very, very similar to the sun appears to have either lots of volatile elements or too little refractory elements. These are elements that condense at very high temperatures. And so it was suggested that this had to do with the formation of the solar system's terrestrial planets. If you turn your protoplanetary disk's complement of refractory elements into planets, it cannot accrete onto the star. And maybe these nearby solar twins, they didn't make terrestrial planets, the material accreted onto the star. So there are other explanations for this observation. It could be this terrestrial planet formation that I already described. It could also be the case that giant planet formation did this. So you can certainly lock up many Earth masses of refractory elements in the cores of giant planets. And the gaps that giant planets open up in their parent protoplanetary disks can also prevent the inward drift of planetesimals or pebbles into the inner solar system, in which they might then accrete onto their host star. It could also be that the twin stars accreted rocky planets. And finally, it's also possible that this is a result of galactic chemical evolution. And so what Chris and I set out to do was to critically evaluate this idea that this had to do either with terrestrial planet formation or with giant planet formation. So before I can get into our experiment, I have to give you a little bit of context. We've seen this already. This is a classic plot that shows the occurrence of protoplanetary disks as a function of age. For star-forming regions that are younger than a few million years, there's lots of protoplanetary disks. Older than about 6 million years, there's basically none. So a planet that has a big gaseous envelope like a giant planet, it has to have formed in these first few million years of its system's evolution. On the other hand, terrestrial planets are thought to take a longer time to form. So you should focus your attention up here on the Earth. So this is a time after CI formation, that is the very dawn of the solar system. It took something like 10 million years for 2/3 of the Earth to form, and maybe the last giant impact took place another 20 or 30 million years later. Maybe Mars, which is a leftover oligarch, maybe it formed in about 10 million years. So terrestrial planets take longer to form. So what is the star doing while this planet formation process is going on? So the structure of a star changes with time. So this is time on a log scale on the x-axis, and this is stars of different metallicities on the y-axis. So a solar-type star is here. So this yellow region indicates that the star is fully convective. That is, one solar mass of material is well mixed. The star reaches the zero-age main sequence after, say, 30 million years, and it has the structure now with only a small fraction of its mass as in a convective envelope. So if you were going to try and perturb the photospheric elemental abundances, it's much easier to do it after about 30 million years than it is to do it before 30 million years. But you'll also note that it takes longer for metal-rich stars, shorter for metal-poor stars, and these metal-poor stars always have smaller convective envelopes than the metal-rich stars. So if you want to look at the subpopulation of stars for which this signal would be largest, you would want to look at the metal-poor stars. Now, this is assuming a solar mass as a function of metallicity. It's also true that mass has an effect to play. So the more massive stars will also have the smallest convective envelope. So if you want to see this sort of signature displayed most strongly, you want to look at metal-poor, massive stars. That's the type of star for which the signal of refractory sequestration in planets will be largest. This also shows, now illustrating it as a different way in terms of metallicity, that the time scale doesn't change very much, but the overall amount of mass in the convective envelope is essentially a linear function of metallicity. That's what this is showing. So if you have a metallicity ratio of 1.6, your convective envelope mass ratio is also approximately 1.6. So it's linear in metallicity. We think we understand the effect of stellar parameters on this trend. Now, what Chris and I did is we went to the systems observed by Kepler to have multiple transiting terrestrial radius planets. That is, stars which managed to form a terrestrial planet system. We used a mass-radius relation to calculate the total amount of rocky material in those planets. And there's a formalism which allows you to predict what the slope of this diagram of abundance as a function of condensation temperature should be. So these are all negative numbers. If the terrestrial planet formation scenario is correct, they should all display a big negative trend. So as you can see in this example, this is that same plot as before with condensation temperature on the x-axis, this difference in abundance on the y-axis. This is the predicted trend if the refractory locking up scenario in terrestrial planets was correct, and this is the actual trend that we see. So the statistical significance of this difference is very large. This is generically what we see. I'm not going to show all of the planets, but I have them in backup slides if anyone wants to see their favorite planet. And what we find is, in fact, the measured slope that we obtain is very, very different than the expected slope. And I should say we can only do this using literature data because we were able to focus on the stars that display the strongest amplitude of this effect. This classical observation was made using a very specialized technique that only works for solar twin stars and requires very, very precise data. Our approach, by focusing at the stars that would display the largest signal, will allow these measurements to be made even with ordinary techniques. Now, I also suggested that it's possible that giant planet formation might do the job. So terrestrial planet formation maybe takes 10 or 20 or 30 million years, but it only locks up a small amount of material in planets. Giant planet formation happens early, which is bad because the star is fully convective. You would have to dilute the impact of the sequestration over the entire stellar mass. But it's been proposed that giant planet formation can prevent maybe 100 Earth masses of material from falling onto the star. So even though it happens earlier, the amplitude of the sequestration effect is larger, and so it's still possible to see it, or it's been hypothesized it's still possible to see it. So what Chris and I did is we went to a sample of stars that had been carefully scrutinized with the Doppler technique for the presence of giant planets. So there are certainly giant planet detections in that sample, but there were also stars that had been carefully screened for giant planets, and no giant planets were found. We were then able to, for every giant planet host star, find a non-giant planet host star that is exquisitely matched both in metallicity and mass. And then among that pair, we could ask, is the giant planet host star depleted in refractory elements as predicted by this idea? And if everything were enhanced, then you would preferentially see the points in this green part of the diagram. And if they were depleted, you'd preferentially see them in this part of the diagram. And what you can see is that, well, it's mostly a scatter plot. It is true that the integrated offset of our entire sample is in the opposite direction from what you would expect if the sequestration of rocky material in the cores of giant planets or the outer solar system because of their gap opening was responsible. So our conclusion is that neither terrestrial planet formation nor giant planet formation is responsible for the apparent refractory depletion of the sun. That giant planet formation is not the answer, terrestrial planet formation is not the answer. I don't have time to go into it, but it's also the case that we think planet engulfment is not the answer, and so we think galactic chemical evolution is the best explanation for the apparent chemical abundance differences between the sun and nearby solar twin stars. So I'll leave my conclusions up and I'll happily take questions.
Thank you, Kevin, for a very nice talk. Questions? Okay, well, yeah, they're in the back.
Okay, my question, thank you for a really nice talk. My question is a little bit complex. The stars that we know that have giant planets that are close in. most of the mass, the refractory mass, is farther out in a protoplanetary disk simply because of geometry. There's a bigger space in the disk. So what you want to look for is giant planets that are farther out that would prevent the refractories from falling into the star. Those might actually be hidden in this population of stars that do not have detected giant planets. Have you considered that?
So the sample we used was Doppler detected giant planets, and in particular, this sample was sensitive to giant planets with orbital separations of about up to about 10 AU. And I think in one of the review talks, it was shown yesterday that direct imaging surveys have shown that giant planets outside of that distance range are much less common than the giant planets that these long-term Doppler surveys are sensitive to. So I don't think that is a major concern. I think that the 5 to 10 AU giant planets that this sample that we used includes would be the main type of thing that would interdict the inward migration of solid material.
Yeah, so if the refractory difference between the sun and the solar twins that are relatively nearby is galactic chemical evolution, then that would mean there are also solar twins that scatter to the other side of that distribution, right? Like they should be on both ends, or are we somehow like on the forefront of chemical evolution in that respect? Like, because the other ones are not as refractory poor, right? Isn't that the premise that are missing them? So shouldn't there be like super refractory rich ones as well?
Well, so there are refractory rich ones. So in fact, the conclusion from the follow-up analysis is that maybe something like 15 to 20% of stars in the solar neighborhood have a similar abundance pattern as the sun. So it is not the case that the sun is singular. It is just the case that it is not. It's this 15 to 20% property is not associated with terrestrial or giant planet formation. Yeah, I'm sorry if I gave you the impression that the sun is singular. The sun is not singular. It's just that it is not the most common abundance trend in the solar neighborhood.
Okay, let's thank Kevin again for the nice talk.